Hello, everyone. Today we are going to talk about non-fusion plasma. So we're going to take a slight detour from the fusion world and talk about other uses of plasmas and other places that plasma exist. And this is kind of a broad overview. We'll go deep into a few things and otherwise remain pretty shallow. So as a first intro, a little about me. My name is Freddie Sheehan. I am a graduate student here at Columbia. I'm originally from New Hampshire. I went to Northeastern as undergrad. I did some low temperature plasma stuff, which we will talk about today. Between grad school and undergrad, I spent 3 years as an R&D engineer at a company called Busick, which makes electric propulsion, which are plasma-based space rockets. We will talk a lot about that today because that is a very cool other non-fusion use of plasmas. And then I'm a third-year PhD student here working on tokamak disruption prediction. So as an intro, first we are going to set the stage and talk about the kind of metrics we'll use throughout the day, throughout this video, talking about different plasmas. So plasmas range a huge span of temperature, and temperature is the average kinetic energy. So it's the same temperature that you're used to. The units get a little funky because what does 1,000,000 degrees Celsius mean? It's kind of hard to grasp, whereas we know what 100 degrees Fahrenheit means. But we'll use these in the same way that you use temperature. So it's the average kinetic energy, it's how fast things are kind of wiggling around. The units we usually use are called an electron volt. I'm not going to go too much into it. But 1 electron volt is about 11,000 Kelvin, so it's about 11,000 Celsius. So it's really hot. And when we talk about kilo electron volt, that's 1,000 electron volt. Same with mega, and those are the usual SI prefixes. So that we'll use that kind of base our temperature. And then density is how much stuff there is per a volume. So in our physical world, things are rather dense. When we talk about plasmas, because as you remember, plasmas are all hot gases, these are relatively low density compared to like a table or even the air around us is relatively high density compared to many plasmas. But it's the same unit. So it's the number of particles per some length cube, so per some volume. And then length scales is a little fuzzier, but this is roughly how big the plasma is. So if the length scale of my computer is about a foot, the length scale of this building is maybe 100 feet, that kind of thing. And we'll talk about different versions of that because the length scale of a plasma this big is only a foot. The length scale of the sun is much bigger. So we'll use these three metrics to kind of ground ourselves because we're going to be exploring a wide range of all of these variables. So this is a image we'll come back to a lot. This is the temperature or energy, same thing, on the x-axis. And again, this is a log scale. So that means the difference between two ticks is a multiple of 10. So going from 1 to 10 to 100 to 1,000. And then on the y-scale, it's density. So you can see that on the order of 10 to the minus 2, which is 0.01 eV, all the way to 10 to the 5. That's a huge range of temperatures. And you can see a similar, we go 10 to the 10 to 10 to the 30 in terms of density meter to the minus cubed. And you'll see things like fire. Fire is a very low ionized plasma. It's kind of on the edge. We won't talk about that today, but it is relatively cold plasma, if you can call it a plasma, somewhat dense, all the way up to the sun, which is very hot and very dense. And even fusion plasma cores actually sometimes exceed the sun in terms of temperature, but are quite a bit less solid. You'll notice these two corners. We won't go there because those aren't really plasmas. If you're too cold and too dense, or if you're too cold and not dense enough, then it's called this interplanar interface. There's like not really enough there to be a plasma. And then same if you are too cold and too dense, you're not a plasma because you're a solid or a liquid, or you don't have enough energy to have ionized, which is what you learned previously. So we'll stay in this kind of band in the middle. We'll move around, and I'll come back to this image quite regularly to talk about where we're going to go next. So right now we're going to talk about plasmas nearby. These are things kind of around us in our world. And you can see these red circles. I'll redo every section. So low energy, middling density. All right, so what plasmas are around us? If you want to stop and think about this for a second, go ahead. But these are things that we interact with on a daily basis, and they're kind of everywhere. So the obvious one is fluorescent lights. These are the tubes that we use as light. There's two electrodes and a very specific blend of gases in there, and it basically creates an alternating current, which is the electricity we get from the wall, and it jostles around the electrons. The electrons collide into neutral atoms, they ionize, and they release light in the process. There is a film on the outside that is used to basically change the color, so there's some kind of conversion there, but there is a very low temperature, relatively high density plasma in a fluorescent bulb. Things like arc welders, if you know what those are, we'll talk a little bit about those. Plasma TVs, which I'll mention briefly. The Great Spindle Microwave, that was a big thing a few years ago, but it's kind of a fun example of making plasmas just in a microwave. Lightning is a very intense, very interesting plasma we'll talk about. And then fire is kind of, I mentioned, it's kind of on the edge. It is maybe a little ionized, but it doesn't really satisfy the criteria of plasma that you learned previously. So it is a bit on the edge. All right, so fluorescent bulbs, as I mentioned, you have this tube of gas and you have two electrodes at either end. You have a cathode, which if you heat up, with this electricity, they spit off electrons. Those electrons are accelerated by this alternating electric field because we're applying a different potential to two different ends. They run into the things, the neutral atoms you have. There used to be mercury. I don't think there's mercury in fluorescent bulbs anymore. There's things like argon. Those excite the atoms or ionize them and they release light. That light is then converted in this coating into the kind of nice white light we see that we get from these lights. And as a note, at the bottom of most of these slides here, I will mention the temperature and the density. You don't have to worry too much about these numbers, but if you're interested in referencing back, you can see kind of comparisons over these. So this is about 1 eV, which is about as cold as a plasma gets, and 10 to the 15 density, which is in the middle. All right, plasma TVs. This is a fun little note that I discovered making these slides a few years ago. Basically, a plasma TV, if you remember, they don't really make them anymore because they were very expensive and hard to move, but they're basically each pixel. So in your computer screen, you have millions of pixels. Your TV is the same. Most of these today are little LED bulbs, but before we had LEDs that were small enough, they were basically each pixel, each subpixel, I should say, because there's a red, green, and a blue subpixel per each pixel that you see on a computer. It was actually a tiny fluorescent bulbs. So there's a tiny plasma in there, and instead of the phosphor coating we had on the fluorescent that makes it kind of this nice white, those phosphor coatings were either red, green, or blue. So these were just tiny, tiny fluorescent bulbs, and that made your pixel, your red, green, and blue, add up to make your pixel of varying colors. So it's kind of a fun side note, and amazing that they could do this on such a scale. All right, lightning. So lightning is an electrostatic discharge, which means there's nothing alternating about it. It's DC current, so it's direct current, and it's caused by a buildup of charge. You have this big, tall cloud that forms because of various atmospheric effects, and what you get is you get two kinds of particles. You get these kind of heavy ice particles, which are falling down because they're slightly heavier, and you get slightly lighter particles, which are going up, and they bump into each other. I should say they're wetter, kind of more watery particles are falling, and the ice is going up because it's kind of like snow. It's not very dense. So they bump into each other and they actually exchange electrons. This is called the Flybow-electric effect. And I have a very fun image. This cat is from the Wikipedia page on the Flybow-electric effect. Basically, when you rub a balloon against your arm or your head and it makes your hair attractive, that's because one side is actually pulling a few electrons off the other side. So this cat jumped into a box of packing peanuts and a bunch of those electrons were stripped. And so then there's an electric charge pulling them together. And you can see if you watch this little GIF enough, you can see the kind of heavy, denser, watery snowballs falling down. They run into the kind of floating snowflakes up, and one gets an electron and one loses an electron. So you get some effect, and over time that builds up. So you get a lot of charge at the top of the cloud, and you get a lot of negative charge at the bottom. When you get a lot of negative charge at the bottom, it actually polarizes the ground because there's kind of this infinite pool of charge in the Earth. And when you have a big electric charge relatively close to the ground, the negatives go somewhere else in the Earth and the positive charges build up. So you have now a potential between the bottom of the cloud and the Earth and the bottom and the top of the cloud. And so what you get is you get this breakdown. And you can see this kind of leading edge. This is this interesting effect. But basically when they connect, so when they make some conductive path, because the air is not very conductive as it is, you get lightning. So that's all of the charge that's built up in the bottom of the cloud, basically running to where it wants to go, which is in this case, the ground. You can also get lightning from the bottom to the top of a cloud. That's when you see lightning kind of going within the cloud and not connecting to the ground. So this is obviously a massive effect. We see it constantly, but when you get that charge breakdown, what it's doing is creating a plasma between either the bottom of the cloud on the ground or the bottom of the top of the cloud. And your plasma is conductive, so once you get that breakdown, which is what we call when we make a plasma like this, then there's an easy conductive path for all those free electrons to go find some positive charge and go to ground. So that's how lightning occurs. So if you had to guess briefly how much current is in the lightning bolt, It's roughly 30 kiloamps on the tens of kiloamp scale. And to give you some reference, a phone charger is 1 to 10 amps, and a tokamak, the ones we're building today, are about a mega amp. So 1 million amps versus 30,000 amps. So it's a lot of current, but it is interesting compared to the tokamaks we build today, which are much more. And the voltage is really interesting because the power of a electric discharge is the voltage times current. So the voltage is very high, millions to billions of volts. And that's what creates that red leader you're seeing. Is you have this massive potential buildup, and that causes the plasma to be produced, and then it gives a pathway. So the temperature actually isn't that hot, but you can see this is very dense. We talked about fluorescent bulbs being 10 to the 15, lightning is 10 to the 21. It's a much, much, much more dense plasma and slightly hotter. All right, we'll go over this one quickly, but if you've never heard of the microwave grapes phenomenon, people figured out that if you put two grapes pretty close together, the other way to do it is you cut a grape almost all the way through, but leave the skin, and you kind of fold it in half, and you put it in a microwave. Eventually, it'll create sparks, and what those sparks are plasma. They're arcs or plasma discharges, and it's actually a very difficult physical effect to explain, but briefly. The microwaves couple with the water as they do normally. That's how microwaves heat food. But because there's some salt content in the grapes, they can actually strip the electrons, and there will be some flow between one grape to the other, depending on what side of the microwave it's on. So then now you have an electric potential, which is the same thing kind of as lightning. And eventually, when it builds up enough, it arcs across. And so that's how you get this kind of sparking. I don't recommend this. I think this can destroy your microwave, but you can see there is a tiny little bridge there. But eventually there's enough of a charge buildup that it will arc elsewhere to try to find the ground. So just a fun little example of a plasma that you can make in your house if you want to risk your microwave. All right, next we're going to talk about industrial plasmas. This is a broad category, a name that I came up with. This is not like a standardized list, but we're moving a little up in temperature, moving a little up in density, and we're going to see how these things are used in various industries. So plasma etching, this is, in my mind, maybe not quite as exciting as fusion, but this is where most plasma physics lives, because as you'll find out in a minute, this is going to make something very important. So plasma etching is a way to precisely cut little channels in a material, and you can use those channels to fill them. You can do it for other reasons, but the main reason is to make little channels. So it uses the concept of sputtering. Sputtering is very common in plasma physics because it's what happens when you get this high energy ion. So when you take an electron off a neutral atom, you get an ion. That ion's being accelerated by some mechanism. This happens a lot in tokamaks, and it runs into the wall. It can break off a chunk of that wall, and that's what we call sputtering. So you can see these secondary ions here, but basically it's, you're firing a stream of pellets at a wall, and you're breaking chunks off. So that's kind of the background of sputtering. And what we can do is we can make this, so this is our chamber. We have our substrate here at the bottom, which we've connected to ground. That's what this symbol is. We make this big, relatively cold plasma in here. We can do this various ways, but we have this big kind of cloud of plasma. And then a lot of times, so in this case, it's created by an RF generator. And then what we do is we bias the anode versus the cathode. So there's some electric field in this direction. So these little ions are being accelerated down towards the substrate. So first we would mask our substrate. So these are things, this is like protective layer. And in this case, we're etching silicon, which might be a clue. And then we have our plasma, and those yellow ions are being accelerated towards the substrate. And you can see the protective layer is being protected, obviously, and then the unprotected layer is being etched away. So it's actually being cut into. So now we've had our big channels cut from our sputtering. And then we can wash off the protective layer. We can make a new mask with that protective layer, etch a different pattern. We can make all these little channels. And I'll ask you briefly, there's been a few clues, but what do you think this is used for? This is semiconductor manufacturing. So the computer you're watching this on, your cell phone, basically our entire world runs off of this process, because this is how we make all those little channels which make transistors in silicon. And silicon is the substrate in this case. So this is a massively important process and is completely critical on plasmas. It's also an active area of research, less in academia because it's a mature industry. Obviously, we're using these products. More in industry, there's a lot of research going to this, but this is probably the most people working on plasmas work on this kind of plasma. So it's something good to know about. You notice that our temperature, we're back to kind of 1 eV, pretty cold plasma. Densities in the middle, 1018, that's pretty dense. But those are both, in this case, actually, you want relatively uniform big plasma, which isn't always the case in a lot of applications. So you want this cloud to be relatively uniform so that when you apply this potential, all these areas are etched evenly. Medical plasma. So this is a relatively new area. There's lots of ideas people are throwing around. This is a new one that I think is being applied in hospitals, but there's a lot of kind of other related things that people are testing. And the problem that this is trying to solve is that there are these things that are called biofilms. So this can occur on scalpels, on other medical equipment, and it's this like really tough layer of stuff, bacteria, old biological material that's kind of hardened onto a scalpel or some other kind of instrument that is being cleaned. And it isn't being able to be cleaned off using normal methods that they use to clean medical equipment. So one way to clean this is by using this little plasma jet, kind of like we were just talking about sputtering, but in this case, we're doing it in air. So you can make these basically scalpels. You flow gas on this outside of this little finger. And this thing is probably about the size of your finger. It's quite small. And then you create a little plasma in here. And you do that by arcing from here to here. We'll talk a little more about a similar process later. But then the flow of gas flowing out of the tip basically pulls the plasma along with it. So this is, I think, unique as you've seen so far in this series of videos, because this is plasma existing at atmospheric pressure. So in the air, you see almost every other plasma we talk about is in some kind of vacuum or some kind of special environment or space, which is also much lower pressure. So this is actually a plasma in the atmosphere, which isn't not unique, but is not used as often. The other thing you can do with this is you can actually use it as a cutting instrument or to like seal wounds. There's all sorts of interesting uses of these plasma scalpels. They're not reused very widely, but it's a new use. So yeah, infected teeth you can also use for disinfection of like biological parts. It's a very precise application of heat and energy, which is otherwise quite hard to do. So again, our temperature and densities are about the same as what we saw before, about 1 eV, 10 to 19. All right, this one is a cool one. This is less of a intentional use of a plasma. It's more of a place plasmas show up in a very cool application and cause issues, so we have to account for them. So when things are falling out of space, they're going really fast because there's no friction in space. And they run into the atmosphere and they create heat because anytime you rub your hands together, you create heat via friction. When you're going really fast and creating a ton of heat, the only thing that's around you is air. So that air is ionized by the heat created by the friction. And so you have this plasma ball around your falling object. So this is what we see when meteors fall out of the sky. This is also why anything like man-made that we want to survive coming out of the Earth needs to have really significant heat shielding. So this is a picture of the bottom of the space shuttle. If you've ever seen a space shuttle up close, I recommend it. These are all these tiny little tiles, about a foot by a foot, that are incredibly interesting. They're actually woven glass because they have to give off heat very quickly, and they burn away intentionally as you get farther down from the atmosphere because it's basically anything we can do to save these things. But it's a very hard problem and something that it took humans a long time to figure out. But we have figured out how to make things survive this plasma environment around a re-entry vehicle. But the other thing it does is now you have plasma, it actually blocks light. And light is also radio waves and any kind of communication that we might use. It blocks because those can't go through plasma of a certain density. We will talk about that later, that phenomenon. But in the case of basically every re-entry vehicle that humans have ever ridden, there's this blackout period. You might have seen it in movies like Apollo 13 or kind of any space movie where they're coming in and there's this period of a few minutes where there's no communication between the ground and the spacecraft. And that's really scary for spacecraft operators because it's also the most dangerous part of space travel. And it's because there is this ball of, this layer of plasma between your spacecraft and the ground. So SpaceX actually solved this recently. I don't think they've used it with any human powered or human spacecraft, but they did solve this. If you know how, you could say to yourself. What they did is they basically avoided the plasma. So if you're falling down, the plasma is below you. And so what they did is they went up, they communicated to a satellite above them, and then that satellite communicated down to Earth. So it's a relatively simple answer, but they did figure it out. And what that allowed them to do was make a video like this. So this is a live streamed video of one of their Starship rockets falling back into Earth. So this cloud you see is plasma. And it's the first time it's ever been filmed. Definitely the first time it's ever been live streamed, which is impressive. But yeah, so this is this really hot, pretty dense plasma that can cause lots of damage to your spacecraft if you do not account for it. By lots of damage, I mean completely destroy it. And so you really have to make sure you know how to deal with that. So this is something that a place that plasmas show up in an interesting way. All right, so next we are going to talk about electric propulsion. If you remember from the intro, I spent 3 years as an electric propulsion engineer at a small company. So we're going to go a little deeper into this because I think it's interesting and I hope you do too. So you'll see we're kind of, again, pretty cold, roughly 1 eV, relatively low density, but we're kind of in the middle here. Fusion edge plasma, less than lightning, maybe more than the aurora, that kind of thing. So relatively cold, relatively low density. So as a brief preface, what is rocket propulsion? So when you think about different ways to move yourself around, we have this not unique, relatively rare situation on Earth where we have this big ball of the Earth under us. So if I want to go that way, I push this way, and the Earth actually gets pushed that way. Not very much, not in the sense that anyone can notice. But I'm pushing the Earth behind me, and so I go the other direction. That's how your car works. That's how we move around in the Earth. But when you lose that, you have to throw something in the other direction. So when you're in an airplane, what it's doing is throwing air behind it with these big heavy fans, and the airplane goes in the direction it wants to go. What if you don't have air? Then you have to bring something, so that's your fuel, and you throw your fuel behind you and you go in the other direction. So this is how all rocket propulsion works. It's kind of the broadest definition of rocket propulsion. And there's a few things to know about it. So first, the heavier the stuff. So if I throw a big rock behind me, I'm going to move more than if I threw ping pong balls. And it's also dependent on what's called the rocket equation, which you might have run into in physics. So this is this relatively simple equation, which is very elegant, which is delta V is your change in velocity. So if I'm going 0 miles per hour in space and I throw a bunch of stuff behind me, I'm going to have some new velocity after that. So VE is the exhaust velocity. That's how fast I threw this stuff out the back. This is a natural log, and this is my initial mass, so mass of me and my fuel. And then the final mass, this would just be the mass of me in this case. We can also rewrite this using this very important term called ISP, which is specific impulse. This is gravitational constant, 9.81 meters per second squared. And then, yeah, so you can basically rewrite exhaust velocity in terms of this term ISP. So we can write it like this. And ISP is very important for electric propulsion because it basically explains why we use electric propulsion. And what ISP is the change in momentum for mass of propellant. So this is my gas mileage. So in a car, you have certain gas mileage, say 30 miles per gallon. That means that car is going to get you 30 miles with 1 gallon of gas. That's how far you're going to get with 1 gallon of gas. It's slightly different because we're talking about change in velocity, not change in distance. But it's a similar effect because in space, all the propellant we use in space, we have to bring with us. We have to bring with us on one of these big rockets, and that's really expensive. So we want this ISP number to be as high as we can. So then there's 3 different examples, and these are kind of the 3 basic ways of rocket propulsion. But if you could think to yourself, how do you think you could accelerate stuff? How do you think I can throw things in space effectively? So the 3 types are pressure, which is this Wall-E image. That's a fire extinguisher. You have a bottle of pressurized gas and you open one end, gas shoots out one way and you go the other direction. You have chemical energy. That's what when you think of a rocket, that's what this is. So you basically spit some fuel out in this big bell, you light it on fire. The gas, because it's hot, because you've burned it, it expands and it pushes you one way and it goes out the other way. And then the final one is electrical energy, and that's what we're going to talk about today. And that's what's showing down here. This is an electric rocket. So what is electric propulsion? It is broadly propulsion via external electrical energy. So the other two, the energy of the fire extinguisher is the pressure. So it's the energy we use some pump to pressurize the fire extinguisher, and then we're releasing that energy. With the chemical rocket, that's the chemical energy in your fuel. Just like you have chemical energy in a log of wood you burn, you're releasing that to make heat. But electrical energy, what we're doing is we're actually getting electrical energy from somewhere else, which in this case is the sun. So we have in this image, we have these big solar panels. Sometimes we have some batteries on here. And then we use that electrical energy to accelerate some gas. And that's what electric propulsion is. We can do this a few different ways, but the way we mostly do it is with plasma. So we know that plasmas, we take electrons off of our neutral atoms, so we get ions and electrons. So these ions now have a positive charge. And if I apply a big electric field, that positive charge is going to go in the direction I want it to, and I'm going to go in the other direction. That's it. That's electric propulsion. You can make these a few different ways. You can accelerate these ions with DC electric fields, which is basically just you hook up some power supply to a piece of metal and turn up the voltage. You can also use it with divergent magnetic fields, which are the magnetic fields that kind of look like nozzles. We'll talk about those later, but there's two different ways to accelerate your plasma behind you and go in the direction you want to go. So where does this energy come from? I mentioned basically solar panels. You can theoretically use a nuclear reactor. No one has done that yet, but if you wanted to go really far away from the sun, say to Mars, you'd probably need a nuclear reactor, so that might be in our future. So how does it compare? We talked about this measure of ISP, which is specific impulse, so that's your gas mileage, and that's the biggest differentiation between the biggest positive for electric propulsion. So a cold gas thruster, which is this, the Wally's fire extinguisher, has an ISP of 30 to 250 seconds. Don't worry about seconds, that's just the unit of ISP. So that's the weight, of a dumbbell, of my laptop, something that we could kind of carry around. So it's a decent amount of force, but not a ton. Then we have chemical propulsion, which is, sorry, I was mixing terms. So ISP is your gas mileage. So 30 to 250 seconds is reasonable. You'll see it's the lowest on this list, but what I meant to say was the thrust, 0.1 to 10 newtons, is roughly the weight of a dumbbell on the Earth's surface. So when you hold something, the Earth's gravity is pulling down. The weight of a dumbbell, a small few pound dumbbell, is roughly 1 to 10 newtons. So that's something that we can experience. With chemical propulsion, you can see the thrust goes from 1 newton all the way up to something like 8 million newtons. And that's the kind of rocket that lifts huge objects off the ground, like the Falcon 9 or the Atlas V, that kind of thing, or the Saturn V as well. So these are these massive chemical rockets. That's how we get stuff off the ground, is using chemical propulsion. But you'll see that our gas mileage is actually not great. It's 105 to 200 seconds. There's some physical limitations there. There's only so high you can make that number go with chemical propulsion. And so we have this other thing called electric propulsion. So the force, the thrust, which is the force that it's pushing, this is a micro, so 1/1,000,000th of a newton, to the biggest ones are about a newton. So the average is about a millinewton, say, and that is the weight of a penny. So if you put a penny in your hand, the weight that you feel is about the force that one of these thrusters is pushing, which is not very much. And you might think, how do we do anything with that? And I'll talk about that in a second. But the really benefit is that it has very high ISP. And that's because when you have an ion, so we made our plasma, we had an ion, then we exposed it to some big electric field, that ion is going to go very fast. It's not very heavy, it's one ion, but it's going to go very fast. And remember, exhaust velocity is proportional to ISP. So we get very high gas mileage. We get going really fast with the amount of fuel we brought to space with us. So why would we only use cold gas and electric propulsion in space? If you want to stop for a second and think about it. So we do that because there is no friction in space. When you're driving a car, every time you push the Earth behind you to go the other direction, if you take your foot off the gas pedal, eventually you're going to slow down and stop. So you have to constantly push yourself because there's all sorts of friction. There's friction in your wheels on the ground. There's all sorts of friction in the car. But when we're in space, if we throw some stuff behind us and we get going 10 miles an hour, there's nothing to stop us. So we're going to go 10 miles an hour forever. So when we talk about these very low thrust mechanisms like cold gas and electric propulsion, as long as we're pushing a little for a long period of time, we can get going really fast. And then we're still going really fast even if we shut these off. So there are much more efficient ways of increasing and changing your speed, which is what you want to do in space. So that's why we use these relatively low thrust mechanisms, but high ISP electric propulsion devices in space. No friction. All right, so there's a bunch of different shapes and sizes. I'm only going to talk about a few here today. You can go explore on your own if you have other interests or if you've heard of other different ones. But they're broadly electrostatic thrusters, which is using a direct current, so not oscillating electric field. So that's something like the Hall thruster, which you see on the top right. This is a little Hall thruster. Gridded ion thrusters and electroplate colloid thrusters, which we won't talk about today. They are technically electric propulsion, but they're a little bit of a subset. And you also have electromagnetic thrusters, which use what I mentioned, a diverging magnetic field to propel to like exhaust your ions. And these can be broadly RF thrusters, which is kind of a vague name, but that's usually what people are referring to, which include helicon thrusters and the Vasimir thruster, which is a very large thruster you can look into, which is very interesting. And then pulse plasma thrusters are similar. All right, so we're going to talk mostly about Hall thrusters. This is what I spent 3 years designing, building, testing, playing with. And they are by far the most used electric propulsion type. So if you run into electric propulsion, it will likely be a Hall thruster. So we're going to talk about how they work. So just to kind of ground you, this little Hall thruster is, you can see my hands, it's about that big. So it's maybe twice the diameter of a can of soda, about as tall. So it's quite small. This is a 300-watt Hall thruster. They go from 100 to, maybe a few kilowatts. And this little kind of channel you see, this one is pointing up, this one is pointing to the right, but that's this yellow thing you're seeing on your right. And you see this little cathode off to the side, that's the cathode hanging off the top. So that's what we're talking about. So what we're doing with this device is we are basically making a perpendicular magnetic and electric field. So we have this big yellow hunk of metal, and what we do is we bias that to some high voltage. So 300 volts, 500 volts, something like that. So that makes an electric field in the direction of this arrow. So out. And also this yellow. Then we make a magnetic field, and that's with this green stuff. So we can do this with permanent magnets. Mostly it's done with electromagnets. So these are, coils of wire that you run current through and they make a magnetic field. And then you can shape that magnetic field with this green stuff, which is just a vague representation of soft iron or any kind of magnetic material. You can shape and form your magnetic field. So what that does is it makes a magnetic field pointing perpendicular from the outside to the inside, or vice versa, but in one direction, but perpendicular to our electric field. So then we have an electric field going this way, or going this way, and then we have a magnetic field pointing up, or in this case it's in, so anywhere in your channel is pointing in, but it's perpendicular everywhere. And what that gives you is your third, if you can see my fingers, that gives you your Hall current, or your Lorentz force, which is J cross B, your current cross your electric field cross your magnetic field, which gives you a perpendicular force. And what that ends up giving you is it gives you a J, and your J is your current going this way. So this is called the Hall current. You can see it like in Hall effect sensors. If you've heard of those, they're used to measure magnetic fields. It's the same concept, but essentially the Lorentz force kind of on mass. So what you get is you get a force on your particles going azimuthally, which is around the channel. So in this case, it's kind of in and out of the board. So why do we care about that? So first step we do is we have this cathode, and our cathode in electric propulsion is our electron source. So we'll talk about this later, but basically it's just spitting off electrons. So they're kind of going all over the place. An electron is negatively charged, so it wants to go towards this yellow positively charged anode. So it gets sucked in here, but then it sees this magnetic field, and it sees the perpendicular magnetic and electric fields, and so it experiences the Lorentz force, and it gets kind of swept into this as azimuthal current. So that's our Hall current. That's why it's called the Hall effect thruster. Okay, so now we have these electrons like whipping around in the channel. Then what? So then we flow a neutral gas. So I'll talk about the different propellants, but we'll maybe say it's xenon right now. So we flow a neutral gas, and so there's kind of this like cloud of neutral gas all around that discharge channel. And then so the electrons are whipped around. The electrons run into an atom of neutral gas, ionize it, so then you have two electrons and an ion. Those electrons continually get accelerated, and you basically get a breakdown, which is basically made of plasma. This is how fluorescent bulbs work. This is how basically lots of glow discharge works. You're accelerating electrons. They crash into a neutral atom. It ionizes. You get two electrons. The same thing happens more and more and more, and eventually you have a plasma. So now you have a plasma. I guess this is what I've just been mentioning. So you have your anode, your cathode. Ion is the natural propellant. So now you have a plasma here, and now all these heavy ions that just kind of appeared. They didn't appear, but they lost an electron, so now they have a positive charge. And then, there's a big electric field right there that wants to push them out. So they get ejected out, and that is what pushes our thruster. That is what is producing force in a Hall thruster. So you're making a plasma in this kind of fun way with the Hall current. That's why it's called a Hall effect thruster. And then once you have a plasma, you have this big electric field which pushes your ions out. That's what this xenon plus is. And then you go in the other direction. In this case, you would go that way. That way. To the left, and the thrust and your exhaust is going out the other direction. All right, so briefly we'll talk about cathodes. These are really important for most forms of electric propulsion, but they're essentially a electron source. They do use plasma, so this is another, it's not making the plasma in the same way the Hall thruster is, But basically what's happening is you have this kind of complicated, um, sorry, you have this complicated, see my mouse? Yep, build. So this thing is, if you can see my hands, it's about that. It's like maybe 6 inches long, an inch in diameter. They're pretty small. And this dark black cylinder, so this is a cross section of a cylindrical device. This dark section is a thermionic emitting insert. So if you heat up a thermionic emitting insert, basically at some point it'll start spitting off electrons. It's a function of the material itself. They're the very fancy materials. So then you have some electrons in here. You're flowing your neutral gas, which is xenon, usually your same gas as you're flowing through your thruster. And then you apply a potential between this outer metal shell, which is actually what you're seeing when you see a cathode. It's called a keeper, and the inner emitter and heater combo. So then there's an electric field pointing between these two. You get electrons pulled out. They run into a neutral atom. You get an ion and then two electrons, and those run into neutral atoms. It's the same process of a DC glow discharge breakdown. So now we have a plasma floating around here. And because we're flowing gas, that plasma gets kind of kicked out. And really what's getting kicked out is the electrons because the ions are getting sucked into here. So now this is you're making a little plasma in here, and then you're kind of flowing your gas out, and that is creating your electron source for your thruster. There are other ways to do this. You can make an RF cathode, so you can make a plasma using some other method, not using this thermionic emission method, and then you have some electrode which pulls out the electrons and keeps the ions. And so it's essentially any kind of way you can make electrons. Hollow cathodes are just by far the most widely used cathode source for electric propulsion because they're quite reliable at this point. All right, so pros and cons of Hall thrusters. The biggest one is they are throttleable, which means you can turn the thrust up and down while they're in space. There's no moving parts. What you're doing is you're changing the flow rate of your gas through the discharge channel, changing your magnets a little to tune the magnetic field, and that can change how much thrust it's outputting. So this is very advantageous. A lot of rockets, chemical rockets and cold gas rockets have one operating point. They're either on or they're off, and that limits the people operating these spacecraft. So that's a nice thing about Hall thrusters. They're quite fuel agnostic, which means you can flow lots of different gases through them, and they work quite well on different fuels, which is also pretty rare for kind of, it's like putting diesel and in your car. Like it's not going to work very well, but this is a car that can run on lots of different kinds of fuels. You can make a lot of different shapes and sizes. You can see this image is actually my hand. So that one is a 100-watt thruster. It's 2 or 3 inches in diameter, all the way up to this Hall thruster at the University of Michigan. You can see this guy. For reference, that thing is maybe 2 or 3 feet in diameter. And each one of those dark circles is a discharge channel. So that's essentially 3 nested Hall thrusters. That's a big one. That's very rare. None of those have ever flown in space, but it's a fun research project. Some cons are you get this exit ring erosion. So right at the edge, you'll see 2 images of Hall thrusters below. These are the same Hall thruster design. One's been run for several thousand hours. One has never been run. And you can see this white stuff is a ceramic. So when you have an ion, if you remember back to our cross section, you have an ion that gets born. Basically, it loses electron pretty far inside the channel. It will most likely go straight out, but it could go out at a slight angle. And if it goes at a slight angle, it might run into something. So the places where those ions could run into a surface, we use this very strong ceramic. And what that's doing is trying to limit sputtering. Remember sputtering from a few slides ago? That's when an ion runs into a material and breaks off some chunks. These ceramics are basically very resistant to that. But they still eventually do break down. You can see this, it looks like it's been blasted away, and that's exactly what's happened just over the course of thousands of hours of operation. And eventually that will cause the thruster to stop working, but it does take a long time. They tend to be quite heavy, these thrusters. So this chamber you can see is about the same size as the one above it. And basically everything that you can't see in there is filled with copper wire. So they weigh several pounds, even though they're not that much. They're not that big. So they're quite heavy. And then the cathodes, which we just talked about, they're very reliable and they work quite well, but they are sensitive. So if they're hot and you expose them to any kind of oxygen or other corrosive gas, they can be damaged. So they're quite sensitive. So another type, which I'll go over briefly, this is kind of a busy slide, but just see what you can, is gridded ion thrusters. So this is also a DC mechanism. So we're not using alternating current or anything to accelerate our ions, but we are using alternating current to generate our plasma. So you can see in this is again a cross section of a cylindrical device. These circles are a wire you can picture being wrapped around this cylindrical chamber. We apply a radio frequency, so a megahertz range signal to those wires, and it makes a plasma on the inside. Once we have a plasma inside, we have these two grids, which are shown by these dotted lines. If I could find my mouse again, these dotted lines. And between the grids, there's a large electric field. So an ion's floating around. I'll get my orientation right. Oops. The iron's floating around this side. I can't do it backwards. And eventually drifts between those grids, and then those grids have a significant electric field, and so the ion gets accelerated. So it's very similar to a Hall thruster, just you make your plasma slightly differently and you accelerate it slightly differently. But it's a similar concept. You can make different sizes of these. This one I'm showing down below is one that I worked on. It's about the size of a tissue box, and that includes all the electronics and the fuel tank and everything, so it's very compact. This is a picture of two of these things firing at once, right next to each other, which is quite cool. In this case, the cathode is this tiny little thing right here. It actually works very similarly to the thruster. It makes a plasma in the same way. It doesn't have grids, but it has another way to kind of kick out the electrons. And that's how that's kind of like the overall. So you have your neutralizer, which is your cathode, and your plasma. And I'll go back and mention something I forgot to mention in the cathode slide, which is in a Hall thruster, the electron source helps seed the plasma for the thruster. So you need that constant flow of electrons to keep the plasma going in the thruster. But there's another purpose, and that's to neutralize your ion beam. So if I'm a spacecraft floating around in space, there's no wires connected to me, and I'm throwing electrons behind me. Just they're leaving. I'm throwing ion, and I'm losing a lot of that positive charge. I will have a buildup of negative charge because, right, assuming I launched neutral, I have the same amount of electrons and ions. If I start throwing a lot of ions behind me, I'm going to have an increasingly negative charge, and that's not great for a variety of reasons. So what we do is we basically, from the cathode, there are some electrons that don't go into the thruster, and they just kind of float around in front of the thruster. And when an ion goes flying by, the electron gets dragged along with it. So that means we are ejecting a neutral talent. Basically, we're losing an equal amount of ions and electrons so that our spacecraft doesn't get charged. So in this case, we actually don't need the cathode to supply electrons to make the plasma, just because of that RF source is a good way to make plasmas, but we do need it to neutralize the ions being accelerated. So pros, you can get slightly higher specific impulse than Hall thrusters, but because you have these grids and you're accelerating things, we talked about sputtering, those grids are going to erode and there's not much you can do about it. And then generally these kind of thrusters have lower thrust than Hall effect thrusters, so that's a downside. So we'll talk about electromagnetic thrusters. I mentioned that these use a different acceleration mechanism, which means instead of using a DC electric field, we actually use a diverging magnetic field. So this is a simplified diagram where you have your plasma in here. You can make that plasma a lot of different ways. Usually you make it with that coil of wire and the RF signal, which I talked about just in the slide before. And then you have this big electromagnetic coil, which again is just another coil of wire. We use lots of coils of wire. But in that case, you're just running a DC current through it, so a steady state current, and that's creating a magnetic field in the azimuthal direction, so horizontal on the slide. But then outside the bounds of the coil, you can see out here, there's no coil, so the magnetic field goes up. You can picture it does wrap back around and connect to its tail on this side, but kind of right outside your thruster, you have this diverging field. And because you have a current going azimuthally, because that's how the plasma is generated, you get a J cross B, so your current cross perpendicular to your B field, and you get a force that's roughly axial, so roughly like straight out behind you. And that's how a magnetic nozzle works. That's another word for this type of electromagnetic thruster. The benefit of this is that you don't need a cathode. So cathodes are, like I said, they're sensitive to a few things. They're also just another piece. When you're flying things in space, you just want to make things as simple as possible. So these are simpler than Hall thrusters. There's no metal exposed, which means you can use corrosive fuels. There's lots of advantages, but the big downsides are low thrust and low ISP. And remember, those are the reasons we use electric propulsion. So if you can't get those, the argument for using these electric propulsion devices gets a little fuzzy. So the other thing you want a really hot plasma. So I mentioned a Hall thruster, most of this field is not that much hotter than a fluorescent bulb. It's 1 eV, 10 to the 15, 10 to the 18, that range of densities, depending on where you are. And in this case, you actually want a hotter thruster, a hotter plasma, and that brings in all sorts of issues. This image down below is this thruster called Vasimir, which I mentioned earlier. This is a specific device that is huge. So these, similar with Hall thrusters, you can make a normal electromagnetic thruster the size of, a water bottle or something like that. But the Vasimier is the size of a big room. And what it has all these different stages. You make the plasma down here with this helicon antenna, with all these big magnets. You heat this ICRH as a way to heat the plasma. So once you have it, you get it really, really hot. You have this massive magnetic nozzle. So this is just a really amped up version of what we talked about a second ago. But it takes a lot of power. And so no one's launched this because it would have to be on a very big spacecraft that hasn't been built yet. All right, so what's the fuel? This is an important part of electric propulsion, so that you can use lots of different fuels, and you're not using kind of normal rocket fuel because you're not burning anything. So what you want, ideally, are things that have high atomic mass. So that means on your periodic table, you're kind of as far down as you can get. Because even though you want the lighter something is, you apply the same force to a ping pong ball, it'll go much faster than if you apply it to a bowling ball. So that means you have higher exhaust velocity, which means you have higher ISP. Remember that ISP is our gas mileage. But in the trade-off of electric propulsion, where you already have really high specific impulse ISP, having slightly higher atomic mass, so your force is greater, is actually kind of the advantage. So usually we want things that have higher atomic mass, because in the grand scheme of things, the force is still not very big, so we want to kind of maximize that as much as we can. So high atomic mass, easy to ionize, that's a really big thing. Some gases are quite difficult to ionize. We don't want to have to spend a lot of energy making the plasma. We'd rather spend our energy accelerating the plasma once we've made it. It'd be nice if it was compressible, which means that when we bring it to space, we don't have to have this gigantic bottle. We can compress it under usually really high pressures into like a relatively condensed gas tank, and then easy to handle. And that's just for, the me's of the world who have to handle this gas and figure out how to deal with it in a safe way just for human testing. So once you're in space, it maybe doesn't matter as much because there's no humans around, but it does make a big difference in terms of cost if the testing can be done safely. So the traditional fuel, which is still effectively the best fuel, is xenon. If you look at your periodic table, it's a noble gas. So that means it is very stable. It's very unreactive. It's also quite far down the periodic table. So that means it's relatively heavy atomic mass. It's easy to ionize. It doesn't store, it doesn't store as like a big brick of something or a fluid, but it stores relatively dense for a gas. And that's what makes it a great fuel. And so it's very safe to handle. You don't want to breathe it, but otherwise it's good in almost every way, except it's quite expensive. Krypton is one step up, so it's one layer up of the periodic table. So it has all this kind of similar benefits, but everything's a little worse. It's slightly lower atomic mass, slightly harder to ionize, doesn't compress quite as much. You need a bigger bottle for the same amount of mass. But in terms of handling, it's the same. It's a totally non-reactive gas. So in that way, it's really good. There's this other fuel called iodine, which is I've done some work with, and it's a very interesting fuel. It's relatively heavy, so it's good atomic mass. It stores as a solid, so it's very easy to store. You don't have to have this pressurized bottle. It's easy to ionize, yeah. So it has a lot of advantages, but it's corrosive, and it's also quite hard to handle. So those are testing capabilities. You also have to make your whole spacecraft and your whole fuel system out of very corrosion-resistant metals, which are more expensive and more difficult to handle, or difficult to weld and things like that. So iodine's more difficult in some ways, but once you get it in space, it's actually very performant, and it's used in that way. It's not used very much. It hasn't been used much so far, but I imagine that will only increase. There are also some ones that fuels you might have heard of being used in the past. They don't really get used anymore, but cesium and mercury, these are both liquid metals. So at room temperature, they're actually liquid metals. So that means they have really high storage density. They're very compressible. They're not easy to handle. Both are quite dangerous, and mercury is poisonous. Cesium is explosive if it's exposed to water. So they are basically off limits for most electric propulsion. But they are very easy to ionize, and they have been tested in the past for this purpose. And then there are some kind of alternatives which are being explored more. Argon, if you'll notice, also is a noble gas. It's very light, so you don't get much force, but it's very cheap. And so it doesn't store very well. It kind of doesn't have all the good characteristics that xenon has, but it's so much cheaper that people are leaning towards using that. And then air is free. You can get it anywhere. It is just a little more difficult. It's quite hard to ionize. It is slightly corrosive. Oxygen is slightly corrosive to some materials, especially when you get it hot. So it has some trade-offs, but people are that's an active area of research of air-fueled Hall thrusters or an electrical propulsion. That was just another image of a Hall thruster running on air. So that's this white plume. You can see that each of these elements has its own kind of characteristic color. And we actually will talk a little about specific line radiation in a couple of lectures. But yeah, they do make fun. All right, so who uses electric propulsion? For a long time, it was, at least in the US, it was mainly government and kind of institutional users, mostly NASA and the Air Force, which is now the Space Force. Some recent NASA missions that have used them are Psyche, which is a very interesting mission that's been launched. It is currently flying towards the asteroid belt to look at an asteroid, which is very cool. It uses a Russian thruster. I'll talk about that in a second. But it was used a Hall thruster that was made in Russia. DART, which was a mission you might have heard of that ran a few years ago, which basically launched this small satellite and they ran it into an asteroid to see if they could deflect it enough that theoretically in the future, if we predict an asteroid is going to hit the Earth, we can launch a satellite at it, hit it, and change its trajectory slightly so that it'll miss. So that had a big gridded ion thruster on it. Actually, the thruster failed, but it wasn't mission critical, so the mission still succeeded. And Artemis is a very cool project, which, if you don't know, it's the long-standing NASA project to put the first woman and the first person of color on the moon. And they are building called the Artemis Gateway, which is basically a mini space station that's going to orbit the moon. And it'll be a stopover point for astronauts going to the moon. So they will fly to the space station, stay there for some amount of time, get prepared, and then from there go down to the moon and back. And that is going to be using 4 Busick thrusters. Busick is the company I worked for, which is quite cool, and 2 thrusters that NASA is building with another company. So that is still in progress. I'm not sure what the launch date is, but Artemis is moving towards, so in the next decade, I think those should be used. There are also other governmental space agencies like the European Space Agency, and then more recently, at least the proportion of number of thrusters being, electric propulsion thrusters being used has been kind of dominated by private companies, mostly SpaceX. So if you've heard of Starlink, many of you I'm sure have, but if you haven't, it's a space-based internet service. So there are lots of these thrusters. This is the top right is actually an image of this. So each of these slabs is one thruster, and this is a whole stack of them. And this is something that you can buy today. You can buy a little dish, and you can put it in your backyard or wherever, and it can connect to these satellites and give you internet. So they're very low relatively. They're quite close to the Earth, and there's lots of them. I think they've launched several thousand, and each of those has a Hall thruster on it. And the Hall thruster is this under this red removed before flight cover. So all these red things are Hall thrusters. SpaceX makes their own, so we don't know much about their specific thrusters, but they do use Hall thrusters. And then these 2 projects, Amazon is doing Project Kuiper, which is the same goal. Again, they're making their own Hall thruster. And then Airbus has a project called OneWeb. Again, the same exact goal, but they actually use Busick thrusters that I worked on. Okay, so what's next for EPO? What are the active areas of research? Big one is high power. So most of the thrusters, like all the thrusters I just showed you doing these kind of internet constellations, are all quite small. They're this big and they're 350 watts, that kind of thing. But what if we wanted to launch a huge thruster? So the Artemis Gateway mission, those thrusters will be by far the biggest Hall thrusters ever launched and operated. Those will be 6 and 12 kilowatts respectively. The image in the middle, this is the Artemis Gateway. So this is the space station around the moon. See the 4 thrusters on the outside are the thrusters that my old company built, and the 2 in the middle are the ones that NASA built. And then this little GIF is one of these thrusters on the outside turning on and starting the fire. So, and that thruster is, you can see my hands, it's quite a bit bigger. It's probably like a foot by a foot by a foot, and it weighs probably over 100 pounds. So those are high power thrusters. People are working on even higher, bigger power thrusters to get things to Mars or to big things, so like big human-rated spacecraft to Mars. That's a very active area of research. There's also better fuels. So iodine is one of those areas of research where we're looking to more space-efficient fuels that are also still very performant. Also things like in situ resource utilization, which is basically if we launch a mission to Mars, it'd be nice if we could gather some CO2 on Mars and use that as our propellant to get back instead of having to bring all our fuel to get there and back the whole time. So that's kind of in situ resource utilization. And then longer life. These Hall thrusters all have limitations because of that sputtering effect I talked about. And so there are different ways that we think we can get around that, but they haven't really been proven. These are some kind of what ifs. A big one that I won't talk about much, but is fun to look into and you can ask us more about is fusion engines. So obviously we haven't figured out how to make fusion make more energy than it puts in. But if we do, and especially if we do in these kind of compact forms like FRCs, which I think you've learned about so far, we take this FRC, we can basically just open one end, and that would be a very good rocket. It would be very efficient, at very high speed and very high thrust. So that's kind of the dream for space propulsion. The other thought is you could use that as both your power source, your electricity source, and your thruster. So it's kind of this combo unit. You don't need an external power source. That means you could go as far away from the sun as you wanted to. This is a really exciting area. Obviously, it's quite far off because first we have to make fusion work, and a tokamak is not going to make thrust, and it's also quite large. So we have to make fusion work on a small scale device like an FRC or a rotating magnetic field thruster. And then we can maybe use it for electric propulsion. This top right image you might recognize from the TV show The Expanse. They actually, in the show, they use a fusion powered thruster. They don't explain exactly how it works, but it's quite interesting if you wanted to, if you had noticed that those are fusion thrusters. There are also things like magnetic reconnection thrusters, which is a very interesting concept. And could be very promising even before we figure out fusion. So this is a small, there are not a lot of people doing this kind of research, but it's very, very interesting. Okay, so we've finished our electric propulsion deep dive. We're now going to talk about some magnetospheric plasmas. Magnetosphere is kind of a layer around the Earth where the Earth's magnetic field is still affecting that plasma, but isn't like the atmosphere that we think about. So the magnetosphere is this layer, yeah, like I said, it's the region around the Earth that's still being affected by the planet's magnetic field. And there's a few different regions. There's the ionosphere, which is kind of a very upper atmosphere after, like way a lot higher than where planes fly and things like that. There's the Van Allen belts, which are these green blobs, which are kind of, they go around the planet like this. They're not spherical, they're kind of belts, which is why they're called belts. And then the plasma sheet, which is this kind of stream of plasma that extends away from the Earth. And I'll just mention recently, it does look like the Earth is flying to the left through space, but what's really happening is that the solar wind from the sun is kind of blowing the magnetic field and all the stuff around the Earth away. So this is kind of like if you had a I don't know, piece of dry ice with a fan on it. That it's all the smoke kind of being blown away, and the sun in this case is our fan. So that tail is always pointed away from the sun. Okay, so we'll talk about the ionosphere. This is an upper atmosphere I mentioned, which is 50 to 1,000 kilometers, big range. 50 kilometers isn't that high. It's much higher than planes fly, but it's kind of on the border of space. And 1,000 kilometers obviously is deep space, or quite a long ways away from space, from the Earth. And then the ionosphere is just this blob, spherical, so it goes all around, of plasma that's ionized by solar radiation. So the light from the sun is enough to heat this gas until it becomes a plasma. There's more during the day than the night. On the dark side of the Earth, there's not much plasma, but there still is a little. And this is important in our day-to-day lives, or maybe it used to be more important, because this is what we use to bounce radio wave transmission. So the Earth is a sphere, and if you wanted to communicate over the horizon, how would you do that? You can't go through the Earth, right? The Earth isn't going to be a very good conductor for your radio waves. So what you do is you kind of bounce it off the ionosphere. And we do that with this very important concept of plasmas, which is that they reflect frequencies of light that is dependent on how dense the plasma is. So I briefly mentioned this earlier, but this is a very important plasma phenomenon that impacts everything anyone does with plasmas, frankly. In tokamaks, we constantly have to consider this. It's a very important concept. So I'll go over it in more detail that is maybe required for this specific application. So the plasmas basically have this natural frequency, which is called the plasma. This is the electron plasma frequency. So this omega is our frequency. And it is essentially the frequency of the plasma would be if you could kind of hit it. If you tap your water bottle or you tap a tuning fork, it's just going to vibrate at some natural frequency. This is essentially the natural frequency of the plasma. And it's dependent on a few things. E is just the charge of an electron, so that's a constant. Epsilon naught is a constant. And N is our density. So at higher density, we have a higher frequency, higher plasma frequency. And then M is, in this case, the mass of an electron. So a constant. So this is dependent on our density. And that means, so we have higher frequency. and for a higher plasma frequency for a higher density. So if the frequency of light is less than the plasma frequency, what do you think happens? So if we're firing, if we have a bunch of photons, or you could think of it as a wave as well, at like kind of incident on a blob of plasma. If the light frequency is less than the plasma frequency, what do you think will happen? So it'll go right through. It's low enough frequency that it's not really affected by the high frequency of the plasma, so it kind of passes through as if it didn't know the plasma was there. And in the other case, you might be able to guess it gets reflected. So if the light frequency is less, oh, sorry, I mixed that up. If light frequency is greater than the plasma frequency, it goes right through, because basically the light frequency is moving faster than the plasma can respond. Then if the light frequency is below the plasma frequency, it will bounce off. Basically, the plasma rejects it and it acts as a reflector. So if we bring it back to the ionosphere, when we have our radio waves, say this is our radio tower, and this is the guy with his phone, we wouldn't be able to go straight through the Earth because the Earth is curved. So what we do is we fire it up, and it bounces off the ionosphere, and then it bounces off the Earth, and it does this kind of pattern, and that's how radio waves work. That's how you get radio in your car. That's how lots of radio transmission works, and it's a pretty important concept. Okay, so what else could ionospheric conditions affect? There are all sorts of things, but it again comes back to the transmission of electromagnetic waves through the ionosphere. So things like satellite communication. So this is GPS. GPS satellites are really far away, and if the ionospheric conditions, which we also call space weather, makes sense. It's changing conditions that affects GPS communication. So if there's certain areas of the Earth that are more prone to these kind of more dense blobs of plasma, and so they have harder time getting GPS readings on a regular basis. Satellite phones and internet, we don't use satellite phones a ton in our day-to-day life, but those Starlink satellites might be affected if that's your only internet source. That could be affected by ionospheric conditions. I mentioned space weather. This is this kind of changing, constantly evolving environment of this ionosphere, and it can affect things like I just mentioned. So there's an active area of research investigating these things. These are some fun figures. I won't go any deeper. Okay, so one you might have been waiting for. This is one of the more known plasmas that we can see with our own eyes, and this is the aurora. So the aurora borealis is in the northern hemisphere, and the aurora australis is in the southern hemisphere, but it's the same effect. Essentially, the sun ejects a big blob of plasma. I'll talk about that in a bit. And it flies towards the Earth. And the Earth has this nice protective magnetic field. And so when the blob hits this magnetic field, it gets diverted because, as you remember from before, the plasma wants to follow magnetic field lines. And so we have this nice magnetic field and purple lines, and this kind of solar wind or coronal mass injection is kind of an instantaneous release, but solar wind is pretty constant of charged particles. They flow along these magnetic field lines, and the magnetic field of the Earth, it's a magnet. So the field lines connect through the center of the Earth. So this plasma flows down those field lines and then hits our upper atmosphere and creates the pretty lights, which is essentially the energy on those particles ionizing the gas in the air. So that's why it happens only in the very top and the very bottom of the Earth. It does occur on other planets. This top picture is on Earth, but the bottom picture is Saturn, and you can see the same thing, because Saturn does have a weak magnetic field, and you can see it. It occurs in the same way. So next we'll talk about the Van Allen belts. These are, you might have heard them in the context of space travel, human space travel, because they can be, you have to consider them when you're sending people through them, say on the way to the moon. But they're these belts of plasma. So they are not uniform around like the ionosphere is. They're kind of, just around the horizontal part. There's the inner radiation belt and the outer radiation, also called Van Allen belts. The outer can have really high energy electrons, this 10 eV even, or 10 MeV, 10 million electron volts. The inner is the ions can be really energetic, but the electrons are slightly less energetic. The fun fact is, like, why are they belts? Why are they not uniform? It's partially because of the magnetic field of the Earth, but it's also because of gravity, because gravity pulls the particles together. But we also think about how they're confined, and this is a really important concept. Remember those magnetic fields that looked like ears? that's essentially a magnetic mirror. So you've learned about magnetic mirrors in the past videos in terms of a fusion concept, but the same effect is in play. So if you take these are two magnets in our magnetic field, or magnetic mirror. So you have particles in here. When they go to the higher magnetic field this side, they say, "Oh, I'm being pushed back," and they bounce back, and they're confined by bouncing back between these two higher magnetic fields. And if we took that and just bent it around and connected those two high magnetic fields, that's essentially a dipole, which is what the Earth's magnetic field looks like. So these particles go, bounce along these lines from the South Pole to the North Pole to the South Pole to the North Pole, and that's how they're confined. That's how they don't leave and go off into space. This causes issue with space travel because the energies I mentioned before, those are really high energy, and so you have to specifically shield your spacecraft to prevent those from hitting people in too high concentrations because it can cause diseases and sicknesses and stuff like that. It's not a huge consideration, but it is something that you have to consider in that the Apollo missions definitely considered. And as a side note, there is a fusion company using this confinement concept to try to make fusion there. It's called OpenStar. It's based in New Zealand. And you can see they actually levitate this magnet. So this donut is essentially the Earth. And you can see it has the same dipole magnetic field shape. And so that's what they're using to confine their plasma, and they're heating it and hoping to get fusion relevant plasmas in that form. All right, next is astrophysical plasmas. Um, the magnetospheric plasmas are technically, within the Earth's influence. These are things outside the Earth's influence. So we're going to talk about stars and then kind of everything else in between. It's a pretty broad range. So the first thing I guess I'll mention that they do scale a whole range of temperatures and densities. So the interstellar medium, which is the kind of space, the nothing between everything, can be considered a plasma, all the way up to the core of a sun or the core of a supernova, which are some of the most intense, hottest, most dense plasmas in existence. So it really is a big range, and this is also, I'll mention, an active area of research. There's a lot of plasma physicists or astrophysical plasma physicists because it's a very interesting field, and you can learn a lot from observing the light that these output. So interstellar medium, it's only a plasma because there's nothing around. Basically, if you have an atom, it's got a few protons and a few electrons. Eventually, there's a chance one of those electrons just leaves. That's a quantum mechanics effect, actually. And so then you have a plasma, and there's no electron to fill the gap because the density is so, so, so low. So that's how an interstellar medium can be considered a plasma. There's no real group behavior like we think about plasmas in a tokamak or in a Hall thruster, things like that. So it's a little iffy, but it is interesting. And then the line you'll see at the beginning of basically every plasma physics textbook is 99% of the observable universe is a plasma. And that's a little why, but also if you do it by mass, it's because most of the mass in the observable universe is in the form of stars. So I actually, when I read that fact a bunch of times, but it occurred to me when I was making these slides that is that intended to be referencing stars because they are observable and they're most of the mass we can observe. And so if you do a quick calculation, so I just looked up this number of 10 to the 53 kilograms. It's a total mass of the observable. So that does not include like dark matter, whatever that is. And you look up the kind of number of stars, the average mass of our stars, and we quickly get a relatively similar answer between our sun is about an average star. So you multiply these two numbers together, you get pretty close. This is an example of a Fermi calculation. Yeah, so because stars are plasma and most of the observable universe's mass is in the form of stars, you can say that it's mostly plasma. All right, so I mentioned this before, but the interstellar medium is basically, everything in between anything else. So the density is really, really low. It's kind of hard. You can write down a number, but it doesn't mean a lot because it's so low density and it varies. And the temperature is, it can be kind of high. You can have high energy particles flowing around. These can be ejected from stars or ejected from supernova. There's nothing to slow them down, so they're flying around out there. And then again, I mentioned before that it ionizes using quantum mechanics. So there's a chance that that electron just leaves. Now you have an ion and an electron, which is, you have enough of them, you have a plasma. You can also get cosmic rays, which can come from stars or supernova, and those can ionize things in space. All right, nebula. I'm sure you've heard of them. They're these big, big, big clouds of gas. and they are quite cold, but they are plasmas. So often, most of these are supernova remnants. You have a star that collapses on itself and explodes, and so all of that mass is now spread out over a huge area, but it's still hot enough to sustain a plasma. You also have planetary nebula. This is when stars just start shedding their outer layers, so it's not a supernova, but it's a similar effect. You get a big dispersal of plasma. Condensed interstellar medium. So this is before there was a star. Gas just kind of starts moving towards its some center of mass because the gravity from all these particles kind of builds up, and you can have collisions that create some heat enough to make a plasma and produce light. Nebula are the birthplace of stars. So these are basically areas where you have enough gas that it can cross a kind of threshold, and that gas will collapse on itself, start fusion in the center, and become a star. That's how stars are formed. They're ionized by EM radiation, so the heat from collisions is also a contributing factor, but the EM radiation from the supernova from other particles can heat up the gas enough to sustain the plasma. These are low density, so 10 to the 9 is one of the lowest numbers we've seen so far. And then 100 it's not nothing. It's not a tokamak plasma, but it's definitely warm. All right, so stars. This is another big area of research and a really thing to understand, especially if you're interested in fusion, which I assume you are, because you're watching these videos. So stars are fusion plasmas. They are the only fusion reactors that work, because none of the ones we make more energy out than we put in. And so we definitely are interested in studying to them. So I guess this is a question, but I did just answer this, how they're formed. You have a big diffuse gas in a nebula, and eventually it reaches some critical mass density, and it kind of all collapsed on itself. And at the middle, there's enough pressure and enough temperature and enough density to cause hydrogen atoms to fuse, and that releases energy, and that causes a chain effect. And that is how a star is not only ignited, but that's also how the energy is sustained. So if you want to answer for yourself how it's confined, how does this ball of plasma stay together? It's with gravity. So the mass of all the gas around itself is big enough that it's constantly crushing itself down. And so it's being confined by gravity. This would be really nice if we could do it this way in a fusion device on Earth, but we don't have enough stuff to do it that way. So we have to use magnets or some other way to confine the plasma. But stars are confined with gravity. They are quite hot. This is 10 to 15 keV. This is about what we are shooting for a tokamak. ICF, which is inertial confinement fusion, does get hotter than that. But it's not that much hotter than the core of a tokamak, even the ones we can build today. They are also very dense. So when we talk about this temperature, it's very hot. It's hot at tokamak, but it's much, much, much more dense. Stars have much more density, and they're sustained. The density is sustained by that the fusion reaction in the middle. I'll just mention, yeah, these kind of two numbers. So tokamak 10 to the 20 is quite a dense plasma, and then ICF is actually not more dense, but is more in the range of the core of a star. But that's a bead this big, and this is a sun. So they're interestingly comparable, seeing as that we as humans can do them on Earth, which I think is quite impressive. So they are very good fusion reactors. They power everything on Earth. Everything goes back to the sun at some point. They also burn a lot of hydrogen. They burn 600 million tons of hydrogen a second. Our sun is young enough that it's still burning hydrogen, so it's still fusing hydrogen, producing helium. As stars get older, once they run out of hydrogen, which is the easiest thing that fuses. As a side note, that's why we are doing fusion with hydrogens, because it's the easiest thing to fuse. It'll start fusing heavier elements and kind of work its way up the periodic table. It produces a lot of energy. It's obviously all the energy we receive. But an interesting number is actually not very energy dense. So if you take the volume of the sun and divide it by the amount of energy, which is 10 to the 26 watts, which is a huge number, but the volume is huge, you actually get a relatively low number, which is 300 watts per meter cubed. A compost pile I found is roughly 1. So it's actually not that much more energy dense than a compost pile. It's just ginormous. And a fusion reactor we are building on Earth is 1,000,000 watts per meter cubed. So that is another issue that fusion is running into, is that we don't have the benefit of these massive length scales on a fusion reactor on Earth. So we have to have it as hot as the center of the sun in the middle, and then 2 meters away have it be cold enough to not melt metal and things like that. So we are doing something with fusion that is actually maybe even harder than what the sun does. All right, sunspots, I'll just mention briefly because they come up in, something you can see with your own eyes if you use a protective telescope or something. But they're regions of concentrated magnetic field. Actually cools the plasma, slightly reducing the light emission. They're also usually active regions. So if you have high magnetic field, you have these magnetic field structures called coronal loops, or prominences. Those are relatively similar. And you also get solar flares. And that's why I mentioned sunspots, because we're going to talk about solar wind next and then solar flares. So the plasma, the sun is constantly ejecting stuff, mass, in the form of plasma from its the outer shell of the sun, and it's helped along by magnetic reconnection, which is those solar prominences collapsing on each other, which I'll talk about next. And it's just a constant emission. And so this is what we call the kind of constant emission solar wind. This is the same image you saw earlier, showing how the aurora borealis or the aurora australis works. A lot of times that is solar wind, but if you get kind of a big ejection all at once, it can make that light brighter, and that's usually when you see, if you live at a slightly more southerly area like we do, you can only see that when you get a big solar coronal ejection. I'll just mention we are protected. So a lot of planets, not only in our solar system, but in other solar systems that we can see, don't have as active a magnetic field. And that might prevent any kind of life from forming on those. The reason that the Earth is so protected is because we have a strong enough magnetic field to divert the solar wind, so it doesn't constantly bombard the Earth. So it's a pretty good benefit. All right, so solar prominences. They tend to happen in areas of sunspots, which I mentioned, but essentially there's these huge arcs. And what's happening is that's basically a big magnetic tube. So as a magnetic field is in this big line, and the outer areas of the sun are a plasma. So the plasma wants to follow those magnetic field lines, and you get these big arcs. And you can see in this picture, this is one of these, it's an artist rendition, but it's one of these big solar prominences, and this is the size of the Earth. So these are absolutely ginormous. You can see them in telescope images on the scale of the sun. And so as you've learned before, the plasma follows these magnetic field lines because of MHD. That's the theory we use to describe that. These are another way to talk about these is flux tubes. So yeah, so this is just another artist rendition, but this is a GIF of these arcs. But then if you have this arc, if basically where they're anchored, those sunspots move towards each other, basically pinches off the magnetic field and then creates this really large release of energy, and it basically ejects that whole cloud, that whole arch of plasma away from the sun, and that's called a coronal mass ejection. And these are huge. It's a huge amount of mass. The numbers are honestly kind of hard to grasp, but they're like many times the mass of the Earth get ejected in one of these things, and that's all plasma. It's this big blob of plasma. The left is an artist rendition showing magnetic reconnection, which is what that pinching process is called. And on the right is an actual image from I think it's the Parker Solar Probe. And you can see like this is the size of the sun. I think it's this white circle. And it's bigger than the size of the sun in terms of area. It's not as dense, obviously. But it's this huge amount of energy and a huge amount of mass. So when these hit the Earth, we get things called geomagnetic storms. They've caused blackouts in the past. This will cause really bright auroras, that kind of thing. All right, so we're jumping a little farther away from home, but another interesting plasma is black hole accretion disks. So I'm sure you've heard of a black hole, but just as a brief review, they are basically clumps of matter so dense that light cannot escape. So you have this really dense ball of matter, and then it's for some radius around it. If light goes into that radius, the gravity is so strong that it pulls the light in. Can't actually see beyond what that's called the event horizon. But slightly outside the event horizon, it's still really high gravity, but things can orbit it and not be sucked in right away. And that's called a black hole accretion disk. This is the same way like the rings around Saturn work. It's the same idea, just much larger scale and higher energy. So as things get sucked towards a black hole, they don't always go straight in. Sometimes they start whipping around. And because the gravity of the accretion disk itself is not insignificant, it pulls all of itself kind of down to this disk. Again, the same way that a ring around Saturn works. That's why it's not a cloud around Saturn, it's a ring, because the gravity of the individual parts of the cloud eventually coalesce into a flat disk. And a kind of a cool side effect, and this is again artist rendition, obviously, but the reason that it looks like it has a top and a bottom. So this is the ring in front of us, kind of on our scale. And the reason that's the top and the bottom is because the gravity is so intense in the black hole that it's actually being bent. So this is the top of the back of the accretion disk. But as it goes over the black hole, it's being bent and shined into our eyes. And this is, again, this is the bottom. So the gravity, these are areas of the universe that are hard to comprehend. But we can actually see evidence of this. So these are two actual images of black holes. They're created with, I think, radio telescopes and lots of computer analysis and lots of math. But you can actually see that it's slightly brighter here, slightly dimmer here, and that's an effect of what we're seeing this is the close side of the accretion disk, and this is the backside being bent over the black hole towards us. We don't know exactly the kind of temperatures and densities, but they are quite dense and quite hot. Again, you see this like KV. We're not beyond the kind of range of the sun or even the range of the temperatures of the plasmas we make on Earth, which is quite cool. But the other thing to note about these is that's really the only way you can see a black hole, because you can't see it itself, so you can only see its effect on its environment, and one of those bright environments is an accretion disk. I'll just add in my favorite picture from the movie Interstellar, which was generated using actual physics codes. So this is as real of a accretion disk as I think you and I are ever going to see. All right, so we are done with the plasmas as you would traditionally call them plasmas. And as a final dessert for our fun presentation, I'm going to talk about quark-gluon plasmas. All right, so you've seen this slide before. You have a solid. What happens if you heat up a solid? You get a liquid. What happens if you heat up a liquid? You get a gas. And what happens if you heat up a gas? You get a plasma. And that's the fourth state of matter. And those are all the four states of matter we ever interact with or see, in our daily life, or frankly, that the universe sees. But what happens if we keep heating up plasmas and we keep heating up protons so much? Is there another step? And it turns out there is. Basically, what happens is that the protons themselves break up. So protons and neutrons are made up of quarks. You don't have to remember any of this, obviously, but a proton is an up quark, and a down quark. They're, instead of charge, so a proton itself has some charge. These have what's called color. That's the up, down, that kind of thing. And the quarks are bound together by the strong force. It's the same thing that binds protons and neutrons together. It's by far the strongest of the four fundamental forces, but it has a very short range. So this is what holds nuclei together. It's also what holds the protons themselves together. So if you heat up a proton so much that those quarks are no longer held by the strong force, they actually break apart and become a cloud of quarks, free quarks being interacting with each other via the strong force, and you get a system that actually acts a lot like a plasma. And so that's what we call quark-gluon plasma. So some analogs are plasma is kind of held together by the electromagnetic force. It's influenced by you can apply external electromagnetic forces and influence them, and they produce their own. So it's this self-correcting behavior, and that's what makes a plasma plasma. The equivalent in this example is the strong interaction, which I talked about. Instead of electric charge, that's color. It's just a name for a property, essentially. And then we have electrons and protons, or electrons and ions in our plasma. We have quarks, and the gluons are the particles that are mediating the force. So this is not something that we think has ever been produced since the Big Bang, because right after the Big Bang, there was not enough energy anywhere in the universe to sustain these things. But they have been produced on Earth at places like CERN and Brookhaven, which are supercolliders. So they basically smash protons together. They get protons going really fast in opposite directions around a synchrotron or around a collider, and then they smash them into each other. And for 10 to the minus 22 seconds, which is kind of hard to fathom, they get plasmas, and I'm putting in air quotes, 4 trillion Kelvin. So that is, again, so far beyond anything else we have talked about today. And we do think that's the first time these things have ever been produced since the Big Bang. These are studied not really by traditional plasma physicists. They're usually particle physicists or theoretical physicists, but it is an interesting extension of what we talked about today. So you can see this bottom left square is everything we've talked about. And then if you go way higher temperature and way higher density, you get all the way up to this quark-gluon plasma. So that is the end of this talk. Thank you for listening, and yeah, have a great day.